Thank you very much. So, yeah, it's a pleasure to be here. My name is Alexander Vosseler. I'm the lead data scientist of the advanced analytics team of Allianz Germany. And the topic of my talk is about explainable unsupervised anomaly detection using Bayesian histograms. So let me briefly sketch the agenda. I will give you a quick introduction to what is anomaly detection, what is the definition of an outlier, and then give you a little bit of a technical background regarding the model that we proposed, and then also show you a Python implementation, BHAD, a package that we have come up with, and then show you some benchmarking, some predictive performances, how the model is doing, and finally give you an outlook and a quick summary. So what is an outlier or an anomaly? So depending on really where and what kind of literature or domain of research you're looking at, you might find different definitions. If you stick, let's say, with the statistics definition, there's a relatively commonly used definition due to Hawkins, which says that an outlier is an observation which deviates so much from the other observations as to arouse suspicions that it was generated by a different mechanism, and this already suggests that there is some sort of data generating process. This is very much statistics based, so really normal data objects somehow follow that generating mechanism, whereas abnormal or deviating objects somehow deviate in some statistical sense from this data generating process. So there are, many industrial applications, obviously, to anomaly detection and outlier detection. For example, fault detection, quality control in predictive maintenance, or weblog analytics when you think of looking for unusual patterns in weblogs. Also in medical, for example, imaging diagnostics, to give you an example, or in finance. So banking, insurance, for example, very common application is obviously fraud detection, in particular for, also important for Allianz, and in natural science, for example, earth science applications, sea surface, temperature anomalies, and so forth. So you can somehow classify the different approaches that are out there in the literature around certain, let's say, categories. One would be if the method you're using is probabilistic in nature or non-probabilistic. On the other hand, it's about the way you can use supervision in your data. So is it an unsupervised, semi-supervised, or even, let's say, some sort of imbalanced supervised learning problem, or something, in between, like a PU learning problem. Is it an ensemble that you're using, or is it a single model? Then how do you measure, let's say, deviation? So, for example, do you use the distances between observations in the feature space, or do you use some notion of density? So number of points in different regions of the feature space, and of course, what kind of data you're looking at. So do you look at a, let's say, cross-sectional data set, or do you have spatial data where you have an index that has a higher dimension? Is it an ordered problem or even a graph problem? So yeah, very much jumping into the algorithm. So Bayesian histogram anomaly detector. Give you a brief motivation around why we have come up with this approach. At Allianz, we were facing, let's say, the challenge that in a corporate insurance context, we wanted to deploy on a global scale, really for different countries, a fraud predictive model. And at that time in that business, we didn't have any, let's say, established business process in place. So there were no labels at all. So this called somehow for an unsupervised approach. And it's very common practice, in particular if you focus on an unsupervised approach, that you should consider an ensemble for this task. And for any black box models, in particular when it's unsupervised, and even more complicated when it's an ensemble, explainability is very tricky and is very crucial, of course, in particular in practical applications when you think of personal data. So the user wants always a reason why a certain score is like it is. So for this reason, we were looking somehow for a sort of a surrogate model, a proxy model that somehow can explain, we can use on behalf of the actual ensemble. And therefore, we wanted to have a model that is predictive on the one hand, but on the other side is really, locally or globally explainable. And so the model that we're looking at is, as the title already suggests, is a probabilistic model, a Bayesian model. So let's dive right in. So let's assume we have observations which are independently and identically distributed from an unknown continuous distribution. And we somehow want to estimate that distribution. And we discretize the support of the random variable y. So we bin it in some sense. And for the simplicity, we assume that the node locations are known at the moment. So this can very easily then motivated in something that we call a piecewise constant data model. So we essentially have to face with certain unknown parameters. So you have those bin probabilities that we denoted by pi, this vector pi. And as I think all of you might know, in a histogram context, it's very crucial, so to say, the number of bins, which is a very crucial parameter that you have to somehow, in a statistical sense, take care of. This is also part of our estimation. So we really, on the fly, also estimate the unknown parameter. And through this binning, this somehow implies that we map the continuous variable yi to a one-hot vector. And this can be perceived as a categorical distribution. So the categorical distribution is very much known to be part of the exponential family, so there exists a conjugate prior, and this will be used subsequently. So a very crucial part, as I said, is here really this parameter k, so an integer parameter, the number of bins, because this very much controls the complexity and the fit of this whole density estimate. And we use an informative prior that was proposed by Scargill 2013. And you can see from the form of this prior that it depends on a hyperparameter, so there's some sort of hierarchy here in place. This hyperparameter gamma controls really the complexity, and we also put a prior on that parameter. And this is an uninformative prior that restricts gamma to the range of 0 and 1. And because this has the form of a geometric series, this controls, so to say, the convergence of this geometric series. And we will use this subsequently then. The parameters pi, which are the bin probabilities, we simply use a Jeffreys prior that can be shown to be a Dirichlet prior with hyperparameters alpha 1/2. And we integrate these parameters out because essentially we want to somehow derive the posterior of the number of bins in order to estimate the number of bins. And therefore we have to integrate the parameter vector pi. This can be done analytically because it's a conjugate model. and we integrate also this hyperparameter gamma numerically, which can be done, for example, by importance sampling or numerically by, let's say, a Simpson's rule or things like that. So just wanted to show you what's the form of this informative prior for the number of bins. And you can see it's highly informative because it somehow restricts the number of bins in a sense that we impose something like Occam's razor, saying that, let's say, more simpler models are preferred over complex models. And this is some sort of regularization that we impose here by this prior. To give you a simple example, how does that work? So how does the estimation process of the number of bins work? We used a relatively famous example from Larry Wasserman, which he termed the Bart-Simpson density. And you can see from the form of this density why this somehow has some resemblance. So under the hood, it's mainly a Gaussian mixture model, a 5-component Gaussian mixture model. And it's straightforward to take some random draws from this. So we take some random draws from this, estimate, so to say, the number of bins, and then compute the histogram. And on the right-hand side, you can see the posterior mass function of the number of bins alongside with the credible interval, 95% highest posterior density interval. And what we term here as k-hat base is the maximum a posteriori estimate. And for comparison, we show some other, let's say, frequentist estimates. So in order to somehow have this a little bit more condensed, we did a little Monte Carlo experiment, and we're repeating this whole process that I just described, so taking random draws, computing the number of bins for 100 times or so, and doing this also with different sample sizes to really, see a little bit the sensitivity regarding the sample size, and computing the mean integrated squared error between the true density, and which we know, obviously, and which is a Gaussian mixture model, and the estimated densities. And you can see that from the figures that, so the red one is the base estimate, so this performs quite decent, I would say. And when you aggregate everything over the different sample sizes, which we term here aggregated mice, then this is very close to Scott's rule, which is a little bit better here. So this seems to work. So actually we want to do anomaly detection, so how can we go there? In a Bayesian context, obviously we need the posterior predictive distribution for a new data point. And this is, again, straightforward to calculate because, again, we are in some sort of multinomial Dirichlet conjugacy, and we can calculate that more or less by hand. Yeah? So this has the form of a categorical distribution. And this is really the probability of a new data point being in the S bin, so to say. Yeah? So it's very simple to compute. And using this posterior predictive distribution as a score, we somehow arrive at the anomaly score, which is simply, we take that as the geometric mean of the posterior predictive distribution. And using a log scale for, let's say, numerical reasons, this we arrive at a simple arithmetic mean, as you can see. And so this very much simplifies many things for us. First of all, the computation, because it's a simple arithmetic mean, so it's linear. The complexity is n times m, where m is, so to say, the number of bins, yeah? And also allows some sort of explainability, obviously, yeah? Because low scores mean being outlierish and vice versa, so we can simply look at the different components, yeah, of the sum and see what makes the most contribution. That's a little bit the idea. And to a quick summary of the algorithm of the BHAD. So overall features uppercase D. We compute the posterior mass function of the number of bins per feature, and then compute the maximum or posteriori estimate. Based on that, compute the sufficient statistics, which are simple counts. Compute the posterior predictive probabilities based on that, do that for all features, and then finally compute the score. So it's very simple to compute. And so there's a package available, BHAD, which is available on PyPy. So this very much follows well-known scikit-learn API alongside the outlier mixin template. And you can use everything that you can use with standard outlier mixin classes. So for example, you can use pipe lines and things like that. So for example, here we use first discretize the continuous features. In case of categorical features, this obviously will be skipped. And then compute the BHAD and compute or predict, so to say, some scores. Coming to the model explainability, as I already mentioned, through the linearity, you can very easily calculate or come up with some sort of local explainability. And for this, we have an explainer module in place, which allows the user to do that. And on an individual level, so really on an observational level, you simply build the rank series of the different log posterior predictive values, and take, so to say, record the feature names and the corresponding ranks, and take this then as an explanation. And on a global level, you can very simply average that. So you take the average rank and then transform this to a unit interval on a global level. And you can visualize that in the usual form that everyone knows from global feature importances. So on the very top, you have the most important feature, and at the bottom, the least important one. So coming to the model benchmarking, we calculated couple of different models to compare BHAD with. So we took, for example, an isolation forest, one-class support vector machines, average KNNs, angle-based outlier detector, then 2 deep learning models, so a vanilla Gaussian VA and a VA with a Dirichlet process prior, so the stick-breaking VA, a local outlier factor, and then 2 very simple model, which is the empirical CDF, a histogram-based outlier detection, which, as the name suggests, is very, very similar to the one that we are using, but on a purely frequentist basis, and doesn't obviously give straightforward inference regarding this crucial parameter of number of bins. And then an ensemble, so a full ensemble, taking the minimum rank of these scores, and a boosted ensemble. I'm presenting here evidence for simulated data, as well as 2 commonly known benchmark data sets. So for the simulated data, we simply took random draws from a 30-variate 2-component student T-mixture. 2 components, because on the one hand, we have, so to say, the inliers and the outliers, and through the mixture approach, we have the latent assignments, and so we can mimic a little bit the situation in a binary classification task, and use the standard instruments that we would use in a let's say, supervised context. And in order to really control a little bit for the uncertainty due to train and test split, we do some Monte Carlo kind of averaging for different train and test split, let's say 100 times, and you average the F1 scores. And the other 2 data sets, so the pin digits, have handwritten pin digits classification dataset and the Wisconsin breast cancer datasets, which we simply, so we take one class, downsample that class, and the other classes are, so to say, inliers. This is also a common approach, so to say, in the outlier literature. And here in red, you can see that the BHAD does a quite favorable job, I would say. So it is here for the simulated, it's among the top 4, and for the other one, it's among the top 3. So again, while having really local explainability. Finally, we wanted to show what is, so to say, the how associated are those different candidate models. When you think of an ensemble, for example, you want to take an ensemble out of all these candidate models, and it's interesting to see how correlated are the different candidates, because if they were not correlated at all, then it doesn't make sense to use that as a proxy model. And you can see BHAD here in the third column from the left-hand side. It's very much correlated with those candidates that we just showed, and even, I mean, obviously with, let's say, the histogram-based in the top row and the empirical CDF, which is somehow to be assumed because they both estimate the density in some sense, but also with more complex models, like, for example, in the top row, the Dirichlet process, VEA, which is a completely different approach to ours. It's a deep learning approach, and but even with such an approach, has a very high Spearman's rank correlation. So this can be taken as some sort of justification to take this as a proxy model. So to sum up, I've just introduced BHAD. BHAD automatically determines the optimal number of bins, allows also using mixed data. It has competitive performance compared to state-of-the-art methods. It allows local and global model explainability due to the linearity in sample size. And there is a Python implementation, BHAD, which can be used via PyPy. And one of the, let's say, on a discussion basis, one of the current assumptions is that the node positions are known, which is obviously some sort of simplification, and that they are equally spaced. And this might lead to some potential inefficiencies, because imagine, for example, you have a high density region, and this high density region, you assign too low number of bins, so you kind of over smooth that region. Yeah? And on the other hand, you might have, let's say, a low density region, and you assign too many bins, so you introduce way too much variance, so you somehow overfit that region. So this is something that is future work, definitely. There are many approaches that you can apply. For example, Bayesian blocks, which is a commonly known method for this kind of problem. So this is really up to future work. So this was it. Thanks for your attention.
Thank you very much for this very thorough and nicely explained talk. There are 3 questions. How weak does it scale in the number of features?
Yes. The number of features you could see is, so to say, just the sum over those bins. Yeah. So let me go back. There you go. So if you have continuous data, yeah, then, so to say, the features are the different bins. Yeah? So the number of bins equals the number of features on a continuous level. However, if you have categorical data, then, yeah, the different levels are, so to say, your different features. And as you can see, they are in some sense linear here. Yeah. So yeah.
Okay, thank you. The problem with anomaly detection is often putting it into practice with a low amount of false positives. How are you using this method at Allianz?
Yes.
Business secret.
Yes. Important question, critical, yes. Obviously, I mean, it's an unsupervised method. Yeah? On simulated data, the world is always beautiful somehow. That was, let's say, a first approach that we used in Allianz for that. And, you know, over time, we collected labels and we switched then to a pure learning approach, actually, yeah? Because we gathered positives. And so we could switch to a pure learning approach and finally to an imbalanced supervised approach. Yeah.
Thank you. Did I understand this correct, that BHAD considers each feature dimension individually, or does it also take into account unusual combinations of features?
Yes, no, that's correct. It's another simplification, of course, makes computation easier, and also introduces, of course, this linearity. Without this linearity, you have a problem with the local explainability. Of course, that's a simplification, but it works quite well so far, and on the benefit of having this local explainability.
Yeah.
Yes.
Yeah. And the last one, can you explain BHAD in a short sentence for a not statistical person? That would be nice.
Well, that's mean.
Exam question.
Yes, yes. Well, yeah, I would say you simply count the number of observations that have a certain value, yeah, in a certain bin. Yeah, probably have to define what a bin is, but yeah. It's a simple count method under the hood. Yeah.
You count the important ones, and not.
Yes, yes. I mean, yeah. It's a Dirichlet approach, so yeah, the sufficient statistic is a okay, sorry.
Obviously. Thank you very much. Unless there are no other questions, let's thank all the speakers again.